All right, hello kiddos. Welcome to our last lesson for the Unit 5 application of integrals. Okay, um, we have learned all about area and volume and how it incorporates integrals in this unit. Okay, we've learned how to take the area between two curves or just the area underneath a curve. We have learned how to take a cross-sectional volume, which we've practiced a few examples of those. And we have learned how to take a rotational volume with disk method. All right, today is all about learning that last rotational volume called washer method. And we're going to learn the difference between the two and the difference between setting them up. Okay? All right, so just a little review of a couple things that we've learned so far. We're going to do this 1998 AB number 1 example. And we're only going to do part of it because, for sake of time. I'm only going to do part A to practice finding the area, and then part C to practice finding the volume generated when revolved about the x-axis, which is what we learned in the previous lesson. Okay? All right, and then part B and D, which is, we've done examples of this before, and I encourage you to try this on your own and check your answers online, but we will do those together when we return. Okay. Okay. So we have a region bounded by the x-axis. So I'm going to sketch this out real fast. I'll do it right here. We have the x-axis. So this horizontal line here. The graph y equals 1 over x, which looks like this and this. Okay. And the lines x equals 1, so right here, and x equals 4. So 1, 2, 3, 4. Okay? So the region that we have is bounded by this line, this vertical line, the curve, and this horizontal line. So this shaded region right here. Okay? First thing first, we're going to find the area of the region, that we'll call that R. And the area of any region is just the difference in the function to the x-axis. Okay? So in this case, this is really old school review here, and I'll write it like this. Area is simply equal to, all right, we can just do top minus bottom here. We can go from farthest left we go is x equals 1 to x equals 4. Okay, those are our bounds to the left and right. Our equation is 1 over x, and then we could say minus 0 if you want. It's the difference between the function and the x-axis. Dx. And that's not a terrible thing to integrate. We know that the integration, just a little review here, the integration of 1 over x is the ln absolute value of x, evaluated from 1 to 4. So this is simply the ln of 4 minus the ln of 1. And the ln of 1 is 0, so this is simply ln of 4. Okay. So this is a review of finding area underneath the curve. But it's part C that I want to spend a little bit more time on. Part C is what we have learned yesterday, the disk method. Okay, look at the wording. Find the volume when we're revolved, okay, when we take this region, and revolve it about the x-axis. Okay, the x-axis is a horizontal line. Okay, so if it's horizontal, that means we're doing top minus bottom. If I were to draw up here on this picture, it means that it's going like this, right? It's going top to bottom. And when we're doing top to bottom, top minus bottom, that is dx. Everything needs to be in terms of x, which it already is. So we're good. All right, so remember what our equation was. Volume equals pi integral a to b of r squared dx. Okay? And remember that the r is simply just the difference from the top to the bottom. So or the way I always like to say it, is the equation to the minus the line of revolution. The difference between the equation and the line of revolution. So in this case, volume equals pi, the integral from 1 to 4, as far left as right as we go. And it's going to be the difference of my equation, 1 over x, to the line of revolution 0 squared, dx. Okay? And then you can ignore the 0. So this is really just pi integral 1 to 4 of 1 over x squared dx. Okay. All right, and we can integrate 1 over x squared all day. If it helps, you can rewrite this as x to the negative second and do power, right? Add 1 to negative 1 and divide to be negative x to the negative first power, or just simply 1 over x if you want to write it that way. But we're evaluating from 1 to 4. So this is pi negative, we'll just say 1 over 4 since it's x to the negative first, minus negative 1 over 1. Okay. And I'm cool with you just leaving it that way, unsimplified is completely fine, and we are good to go. Okay. So just to give you a visual of what we just found here, and to show you again what's happening, I'm going to use that website. So on this website, I've actually graphed 1 over x between 1 and 4. You can see that clearly with this red line here. And I've made the shaded region between the curve and the x-axis. All right, look what happens when I revolve it. That's what it means to revolve. It's sweeping around, and then that shape it makes. Oh, it's not going to let me grab it. The shape it makes is this 3-dimensional figure, okay, where the cross sections are circles. That's a revolution volume. Okay. All right, so there was that. So a good little review of yesterday's lesson. Let's move on to today's stuff. It's still going to be a rotational volume, but there is a difference in this one. Yesterday there was no gap in our volume. Volume by washer means we will have a gap in our volume. And I want you to kind of understand what I mean there. First of all, a washer is a tool or a piece of equipment used, in building and stuff. A washer just looks like an open circle, right? It looks like a little CD looking thing. So there's like a gap in it. That's why they call it washer method. But what I want you to write down and simply understand is that washer method is used when you have a gap between your functions, function or function is plural, and the line of revolution. Okay. So for instance, in this previous problem, how you can always tell is you're going to look at your bounds and you're going to look at your equation. In this case, I'm trying to find a different color, sorry. Your line of revolution, if I were to take it from point A to point B, notice how the shaded region is touching the entire line of revolution. Okay, so there's going to be no gap whenever you revolve it. Look what happens with washer method. Let me give you an example. Let's say, for instance, we have, and I'm just going to make up 2 drawings here. Let's say you have like this is f of x, and let's say this is g of x. Okay, and maybe they go on forever, but we're looking at it between these two functions. And let's say the shaded region is the region bounded by the 2 functions. Okay. Well, what if my line of revolution is the x-axis? What if I ask you to revolve this about the x-axis from point A to point B? Okay. Well, notice what happens. Okay. It's going to revolve about this line like we showed on that website. It's going to kind of reflect its shape down here. It's going to make this 3-dimensional figure, right, with its shaded region over here. But notice what happens as it revolves. You see how there's this big open gap right here in the middle, okay, where there is no volume. So then we're going to have to find the volume a little bit different. How you can tell is if you take your line of revolution and go from A to B, if any piece of the shaded region is not on that line of revolution, it's going to be a washer method. Look at all this white space here, all that gap here that's not going to be covered. If I were to draw out this three-dimensionally, it would look something like this. Okay, so it makes this three-dimensional shape, but you almost have this like gap. I'm trying my best to draw the gap if I can. You almost have this gap on the inside of it. Okay. Well, there's a simple fix to it. It's kind of like just a little bit extra step of doing disk method. All you're going to do is take the volume rotated by the outer function and then subtract the volume rotated by the inner function. So basically what I'm saying is you're going to do the volume of the entire thing as if there's no gap, and then subtract out the gap. So in this case, we're going to have two volumes that we're subtracting. The volume of the entire thing, okay, subtract the volume of the gap. So we need to have two volume equations. One with a radius of the outer function, which would be top minus bottom, or in this particular example, this would be the big equation f of x, the one farthest away from the line of revolution, minus the line of revolution. Okay? And the radius of my inner function, that I'm also going to need to know, is going to be the top minus the bottom of my closer equation to the line of revolution. Okay. So then the equation becomes just two disk methods. So the volume is going to be equal to pi, the integral a to b of, I'm going to say r sub 0 for my outer radius, and I'm going to subtract the volume of my inner radius. So pretty much I just did two disk methods that I'm subtracting from each other. Okay. Now to save ourselves a little bit of time and space, since they share pi integral a to b, pi integral a to b, we can write this as one integral. So we would say the radius of the outer squared minus the radius of the inner squared. And this right here is your equation for washer. Whereas for disk, remember, there's no gaps, so you only need one volume equation. That would just be a to b of just your regular old r squared. Okay. So let's look at a couple of examples. See how many examples we can get through. Okay. It says, find the volume of a solid created by rotating this equation and this. Okay, so by rotating that and that, so bounded by that region, about the x-axis when we're between 1 and 3. So the wording doesn't say do washer or do disk. The wording is the same as yesterday's wording. You're just going to have to decide which of the two equations to use based off of how it's rotated, based off if you have a gap or not. So let's start by drawing. Okay, it's always the first step. So I'm going to draw, let's do x squared plus 4 first. X squared plus 4, let's see, is just the x squared equation of 4. So there, something like this. Okay. All right, so we got that as one bound. We got the line y equals 2, so there's y equals 2 right there. And we're looking between 1, which is right here, and 3, which is kind of off the graph here. So I'm just going to say that right there. Okay. So what's bounded is this region right here. We're between y equals 2, x squared plus 4, and between 1 and 3. So I took all my bounds and I shaded the region that's bounded between the two. Okay. Now, what's happening is it wants me to rotate this about the x-axis between 1 and 3. Here's 1 and 3 on the x-axis. So I'm going to label my line of revolution in blue here, the x-axis between 1 and 3. If there's any part of the line of revolution that is not touched by the shaded region, there's going to be a gap in the volume. So notice how none of my shaded region touches my line of revolution. That means I'm going to have this hollowed out circle in the middle. It's almost going to make like some type of like traffic cone looking shape. Or someone last year called it a Christmas tree stand, and I'll show you what I mean in a second. This is going to be rotated about this line, so it's almost going to reflect the same shape over here. Okay, it's going to kind of reflect the same shape over here. It's going to make this three-dimensional picture. Let's look at what this looks like on our website real quick. Okay, so right here, I graphed all of the bounds. I graphed the line x squared plus 4 and the line y equals 2, and I did it between 1 and 3, and I chose the region between that as the shaded region. And then I made it to where we're revolving this about the x-axis, so across the line y equals 0. Watch what happens. So we take this shape, and it's revolving all the way around. So it doesn't do the best job. So really, it's filled in between that green circle and the blue circle. The only hollow spot is inside the green circle, but everything should be shaded between the green circle and the blue disc here. And someone was like, oh, it almost looks like a Christmas tree stand. I was like, yeah, that's kind of what it looks like. But everything's filled in but that green circle in the middle. So, so yeah, hopefully that kind of makes sense. All right, let's do it one more time. We're revolving it. See how they're revolving it around the circle. Everything's filled in but inside that green circle. All right, well, because there's a gap, we're going to have to set up our equation here. So in order to do this, remember that, that because we're revolving about a horizontal line, it's top minus bottom. It's top minus bottom, so this means dx. Okay? So let's talk about our different radiuses. We're going to have a radius of an outer, okay, and we're going to have the radius of the inner. Now, the radius of the outer is just the outermost equation to the line of revolution. The outermost equation is that x squared plus 4 minus 0. Okay? The outermost equation minus the line of revolution. The innermost equation, the bottom of the shaded region, is the line y equals 2 minus 0. Okay, so those are our two radiuses. So then our equation for volume is simply going to be the integration from 1 to 3, our leftmost bound to our rightmost bound, okay, of the top function, volume, I guess, or the outermost function, which would be x squared plus 4 minus 0, which I'm not going to write, squared. Okay. Remember, this is the radius of the outer. And then we're going to subtract off the volume from the radius of the inner, which is 2 minus 0 squared. Okay, this is the radius of the inner squared, dx. Okay. And if we can solve that, we have what that volume is going to end up being. So we got pi integral 1, 2, 3. I'm going to reduce this to x to the 4th plus, that's going to end up being 8x squared. If I do that, plus 16 minus 4 is 12. Okay, so I just went ahead and combined that 4 with the binomial expanded there. Okay, and that integral is nothing terrible to solve. It's just a polynomial. So we get to this pi. It integrates to 1/5 x to the 5th plus 8/3 x cubed plus 12x. Now, this is not an example where one quantity is going to cancel out because we have 1 and 3, so we're going to have to write out the whole thing. And this would be like a calc inactive. I would just leave it as 1/5 3 to the 5th plus 8/3 3 to the 3rd plus 12 times 3. I would do all of that, subtract everything with a 1 plugged in. So 1/5 1 to the 5th. Plus 8/3 1 to the 3rd, which is just 8/3, plus 12 times 1. Okay. So we have everything with 3 plugged in, subtract everything with 1 plugged in. That's washer method. Okay, so there we go. Let's try to get a few more examples in if we can. I got quite a few more, but we'll just see what we can get in. I'll try to keep it to the same length as the last one. Oh, I love this problem. The wedding band, okay, can be created by rotating the region bounded by the function x squared plus 2 and 4 minus x squared about the line y equals 1. Find the volume of this shape. This is really cool looking. So let's first graph it to make sure what the problem looks like. And you'll see that it is indeed a washer method. Okay. So let's do our axes. Let's start with the equation x squared plus 2. So I'm going to go up to, just right here, and it makes this equation right here. Oops. Okay. So there's x squared plus 2. 4 minus x squared is shifted up 1, 2, 3, 4, and flipped. So it looks something like this. And you can see that the graphs are intersecting at the points 1, 3, and negative 1, 3. Okay. So the function, the region that we're looking at is the region bounded by those two functions. So this region right here. And it wants me to take that region and rotate it about the line y equals 1, which is right here. Now notice, okay, we're looking between negative 1 and positive 1 because that's where my graphs intersect. Notice how at no point is my function touching the line of revolution. So when this rotates, there's going to be a gap or a hollow point. So when it rotates, it's going to kind of rotate and make the same shape on this other side. It's going to make a ring-looking shape. Again, let's look at this on our website so you can see exactly what I'm talking about here as it rotates around. Okay, here we go. So I got my functions graphed, and I chose the region enclosed by them to be what's going to be revolved. And we're revolving it about the line y equals 1. Watch what happens. Look at that. It's making a ring-looking shape. Isn't that cool? A ring-looking shape. So that looks like a wedding band almost. That's kind of the point of this problem. All right. Let's figure out what that volume is. So we'll discuss the radius outer again. The radius of the outermost function away from the line of revolution is this part of the graph right here, the top of the function, which is the graph 4 minus x squared. So it's 4 minus x squared is my outer function minus my line of revolution, which in this case is 1. Okay, so that's like the top minus the bottom, right? That's kind of how I want you to think about it. The equation to the line of revolution. The radius of the inner function is the part of the function that's closest to the line of revolution, so that bottom part. So that function was x squared plus 2, subtract the line of revolution. Okay? Which if you want to simplify both of these, you can say this is 3 minus x squared, and you can say this is x squared plus 1 if you want. Okay? So then remember the equation for volume for washer. It's the integration from a to b, so I'm just going to write it out, a to b, of my outermost radius squared minus my innermost radius squared. Okay? So in this example, we're looking between negative 1 and 1. That's where they intersect. We are doing our outer function, our outer radius was 3 minus x squared squared. And my inner function was x squared plus 1 squared. Okay. And then it becomes, again, another thing that we can simplify and integrate. So we can take a second and do it real quick. I'll at least simplify it out for you. It's 9 minus 6x squared plus x to the 4th minus x to the fourth plus 2x squared plus 1. And I think this actually reduces down pretty nice. I'll let you pause the video and try it on your own if you want to. But I'm getting 8 minus 8x squared for when it simplifies. And then you can integrate and solve. Okay. Actually, there's a GCF of 8 we could actually take out to make our lives a little bit easier if you want. So that's nice. And then the integration of 1 is x. The integration of x squared is 1/3 x cubed, evaluated from 1 to negative. Okay. Now, for sake of time, I'm going to let you plug 1 into that, then minus plug -1 into that, and that's your final answer, okay? The final answer is on the completed notes. I encourage you to look those up. Okay. On to the next example. It says, find the volume of the solid created by rotating the region bounded by this equation here, and y equals 4 about the line x equals -2. So let's graph our region first and understand exactly what this is saying. Let's start with x equals y, the square root of y, which if you want to square both sides, this is the same thing as y equals x squared, but it's going to be the positive side of x squared. So for instance, it looks like this. Over 1, 1, over 2, up 1, 2, 3, 4. The region looks like that. That's the square root of y. That's x equals the square root of y. It's the same thing as x squared equals y, but again, just the positive side of it, because you can't take the square root of a negative y. Right. So that's our first bounded region. Our second bounded region is that it's at y equals 4, which is this line right here. Okay. And then we're gonna take this region here, and we're gonna rotate it about the line x equals -2, which is right here. Okay. So this region around this vertical line here. Again, if we look at our line of revolution, at no point is that touching any part of my shaded region. So there's going to be a gap between this function and this line. Okay. All right, but notice the difference. It's around a vertical line, so we're going from the right to the left. Okay, right minus left for our radius. Right minus left. Okay. Remember, when it's right minus left, when my line of revolution is vertical, both of those mean that this is a dy equation. Everything is in terms of y. Okay? So the outermost function away from my line of revolution is that equation, the square root of y, which is already in terms of y. So we're good there. So my outer radius, okay, is the square root of y minus my line of revolution. So I'm just going to say, to help us out, y to the 1/2 power, I'll go ahead and say that. Subtract my line of revolution. Okay. Or plus positive 2. The radius of my inner function would be this equation right here, the leftmost bound, I guess, the one closest to my line of revolution, subtract my line of revolution, which this left side of this graph here is 0. X equals 0 minus my line of revolution, -2, or simply 2. Okay. So that's going to take the volume created by the outer, subtract the volume created by the inner, and we're going to be left with the volume in between the two. Okay. So remember, simple formula. Volume equals pi, integration from A to B. Now it's going from the most bottom point to the most top point whenever we're revolving around a vertical line, right? So we're going from the lowest point at 0 all the way up to that horizontal line 4. Of my outer radius, or y to the 1/2 plus 2 squared, subtract my inner radius, or just 2 squared, dy. Okay? So then we have pi integral 0 to 4. If I were to FOIL this out, we have y plus 4y to the 1/2 plus 4, and then minus 4 dy because of that. And those go bye-bye. So it's a pretty simple integration from here, right? Actually, I'm going to go ahead and integrate it. Y is 1/2 y squared, and 4y to the 1/2 is 8/3 y to the 3/2 power. Okay. And this is evaluated from 4 to 0. Again, plug 4 in for y, plug 0 in for y, subtract the 2, and you have your final answer. The final answer is outlined on our website. Okay. All right, these have all been really good problems here. I think I'm going to have to, it's 31 minutes in, I think I have no choice but to save the rest of the examples for our review day. So these two and this one. On our review day, I'm going to finish all the examples that we didn't do in the video lessons of the washer method and the disk method. Okay? So you should be all set with those. If at any moment you need any help with anything, please reach out to me. And also, here's just a little chart that I found online to summarize all of our volumes. For instance, volume of a revolution. So you have disk and you have washer. You just use pi r squared for disk method. And for washer method, we have to have the radius of our outer subtract the radius of our inner. So this is just a summary chart here. And then I also put a cross-sectional summary chart. So a cross-section, if it was a square, quarter circle, semicircle should be pi over 2. That was a typo. Equilateral triangle, isosceles right triangle, and a diagonal in XY plane, which we never do that. But here you go, little summary chart. Try use some of these problems here. And you now have enough information to complete your Delta math assignment. Okay, so I believe I made it 6 problems, 5 or 6 problems. 2 disk, 2 washer, 1 cross section, and 1 area. So yeah, 6 problems. You should be able to do all of it now. So best of luck. And if you need any help on it, please reach out to me. All right, I'm done then.